Because now let's start taking a look at some of the energy-water relationships. Every time you use 1 kilowatt hour of electricity with a normal combination of what we have today of natural gas, coal-fired power plants, you're evaporating about 0.4 gallons, or just say roughly half a gallon of water is being evaporated to cool that system. What does that mean? We all know everybody's been going around putting LED traffic lights in. You're replacing a 130-watt bulb with a 15-watt bulb. Every 3-bank light up there saves about 1.5 gallons of water a day from being evaporated. Now, there's another tie-in with water and energy. As we go through here, nuclear is less thermodynamic efficient, so you don't get quite the bang out of your buck on water. You're using 0.5, 0.7 gallons. Look what happens if you go to coal-fired power plants with sequestration. The technologies out there require the use of water, and consumptively you will double your water use per kilowatt hour with sequestration. And you get to geothermal because it is of lower temperature, and people that understand Rankine cycle thermodynamics understand that it's less efficient, so you have to evaporate any more water. Well, that's electricity. Bottom line is what we have now. We have the top end of the chart is what you see the solar thermal and everything up there. The top end of the chart and the very bottom end of the chart are our two choices for two types of choices for future energy for electricity. And you can see that photovoltaics and wind, they're dry people. They don't use any water at all except in the manufacturing of the equipment itself. So that's the thought process. Now let's go and take a look at the water needed to produce all these new energy sources that we're going to be looking at. And here you can see, look at this, biodiesel. If you're irrigating the soybeans to make the oil, to grow the soybeans to make the oil, it can be 2,000 to 3,000 gallons of water for every 1 gallon of biodiesel. If that's ethanol, and remember their mantra, and I love their mantra, it's drink the best and burn the rest. If you're doing with irrigated agriculture, you're at 1,000 gallons per gallon, or 10,000 gallons per million BTUs, as opposed to, when you get back here to some of these other things like normal petroleum extraction and refining, where you can use about 1 gallon per gallon type stuff. Another big one that's coming out, enhanced oil recovery. Because you're using all these water floods and everything, you do consume a lot of water. Luckily, a lot of this water can be brackish water that was produced from a brackish water formation. Bottom line, it takes a lot of water to supply us with energy. That's the whole thing I'm trying to show here. The hydrogen economy we talk about, the major source, you can either make hydrogen by taking petroleum or gas and extracting the hydrogen molecule off the petroleum, off the hydrocarbon. Well, it's the hydrocarbons we're trying to get away from in this. We're trying to go away from hydrocarbons to have something else to burn to make hydrogen. The only other major source of hydrogen is water. You have to split it, and you have to do it. An electrolysis cell, incidentally, with a name like Hoffman, I will tell you that that's done in a Hoffman cell. August Hoffman developed the process. Enough of that from the Hoffmans here. Solar thermal. Everybody is really whoopee on this. Go out there. Yes, the energy is out there. You focus the mirrors up there. You make steam. You have to condense the steam. If you're using a standard Rankine cycle thermodynamic process, you're using a cooling tower or something out there to cool it. A lot of companies have tried to place these where the sun is the best in the southwest, and have been told, no, you can't put it here because we don't have enough water. You keep seeing we keep bumping the two resources up against each other. That keeps on going. Look in Texas. If you take a look at the biggest oil producing state in the union, and you look at all their water use for all industrial uses. Now this doesn't include hydroelectric, which you're simply passing the water through on down the stream here. But if you look at this, and you look at all the water used in industry in the state of Texas, a large portion of it has to do either with producing electricity or recovering and refining oil and gas. The rest of it, chemicals particularly, and pulp and paper making, you name it, cooling tower and boilers, that's the next biggest use of water. Only about 22% of it is used for everything else. There's a lot of connection between oil and water. Again, this is the purpose of this talk, is just to bring these things to your knowledge. Now, we learned this morning that in Las Vegas, and thank you, Doug, on this one, that it takes about 6.5 kilowatt hours per 1,000 gallons of water. That includes water and wastewater, correct, Doug? Just water. Okay, so 8 kilowatt hours every time you flush a 5-gallon flush toilet. You have used 40 watt hours of electricity in the process if you go to Las Vegas. Now, I wouldn't want to be a betting man, but I bet you that's a lot of power at the end of the day, just like he pointed out with the turf. That was a beautiful example. With 2 inches of turf, your carbon equivalent is equivalent to what you do for a lawnmower and stuff. That connection was great. But you have this across the United States. It's around 4 or 5 kilowatt hours per 1,000 gallons. There are places in California where it's as high as 20 kilowatt hours per 1,000 gallons, or 20 watt hours per gallon. That's a lot of water, people, and a lot of energy. You notice I said that both. It's a lot of water to generate the energy to move the water. Part of the point of what we want to make here. In fact, they did a study in California, and here's one that will blow your mind, with natural gas. 32% of all the natural gas used is directly related in some way to water. It's either used to pump the water for the irrigation, the residential, commercial and things, or used to heat the water, etc., like this. We're connected at the hip, and there's the same thing, 19% for electricity nationwide. It's only probably about 8 or 10% nationwide, but that's still a huge amount of all the electricity that we generate goes directly into doing something with water. So, wow, these connections are there, and they're real, and they're going fast. So what are we going to do about this water situation? Well, number one, we're using water right now primarily from precipitation, freshwater sources. That is available to us represents less than 1% of all the water that is available on the earth. So what are we using here to get the energy out? This is just looking at water supplies. If you're pumping it from a well or you're using surface water, you're around, just think 2 kilowatt hours, 3 kilowatt hours per 1,000 gallons, unless you're over there and wanting to go gamble over in Las Vegas, and it's a lot more than that. Desal, look at the red one out there. 12, that is a good, efficient system. It's 12 kilowatt hours per 1,000 gallons just to desalt the water. And the interesting thing is, if you look at the distillation side of it, the energy uses come out to be very much the same in the total number of BTUs that are out there. If you happen to live on a coast, that's where your next big water resource will come from if you're running out of water. By the way, the state with the largest amount of desalination capacity in the United States is Texas. That has 80 million gallons a day of desal capacity. And that includes the largest desalination plant in the United States in El Paso. If you know your geography, that's as far from the water, from the coast as you can get in Texas. They are desalting brackish water. Why are they doing that? They're flat running out of new freshwater resources. And so a lot of things are happening out here, and everything that you look at. If you go to reclaiming water, again, you're putting more energy into that water. That reclaimed gallon has all the embedded energy that we talked about before from the water and the wastewater side of the thing, plus the energy that it took to treat that water to high enough quality and pump it back for the reclaimed water. So the embedded energy in that gallon going all the way through is even a little bit higher. Now, if you look at it just from the reclaim standpoint, though, usually its total energy is not any more than it is for the fresh water, or even less. So you have to look at these things carefully to break them down. And I just get down saving water saves energy, save energy saves water. Well, most of the time we can see there are conflicts coming.